Welcome to our deep dive into amplitude modulation, or AM. In this video we'll explore what AM is, how it works, and why it's such a foundational concept in communication systems. From its basic principles to its practical applications, we'll break down everything you need to know. Whether you're a student, a hobbyist, or just curious about how radio signals are transmitted, this journey will help you understand the core ideas behind AM. Let's start by looking at how AM represents information in both the time and frequency domains, setting the stage for a comprehensive exploration. Amplitude modulation, or AM, is a technique used to encode information onto a carrier wave by varying its amplitude. This means the strength of the signal changes in proportion to the information being sent, such as audio or data. AM is one of the earliest and most widely used forms of modulation, especially in radio broadcasting. Understanding AM is crucial because it forms the basis for many modern communication systems. Next, let's see how AM signals appear in both the time and frequency domains, which will help us visualize the process. The time domain, an AM signal looks like a high-frequency carrier wave whose envelope or outline matches the shape of the original message signal. Imagine a fast, regular wave whose peaks and troughs grow and shrink according to the information being transmitted. This visualization helps us see how the message is embedded within the carrier. By analyzing the time domain, engineers can assess how well the signal represents the original information and identify any distortion. Next, we'll shift our focus to the frequency domain for a different perspective. The frequency domain, an AM signal, is represented by its spectral components. The carrier frequency sits at the center, with two sidebands on either side. These sidebands contain the actual information from the original message. The frequency domain view is essential for understanding how bandwidth is used and how different signals can be separated or filtered. This perspective also helps in designing systems that minimize interference and maximize efficiency. Now let's discuss the modulation index and how it affects the AM signal. Modulation index is a key parameter in AM. It measures how much the amplitude of the carrier wave varies in response to the message signal. A higher modulation index means more pronounced changes in amplitude, which can improve signal clarity but also risk distortion if it gets too high. Conversely, a low modulation index may result in a weak or unclear signal. Finding the right balance is crucial for effective communication. Next, we'll see how the modulation index relates to the bandwidth of an AM signal. Bandwidth refers to the range of frequencies an AM signal occupies. In standard AM, the bandwidth is twice the highest frequency present in the message signal. This is because both the upper and lower sidebands carry the same information. Understanding bandwidth is important for efficient use of the frequency spectrum and for avoiding interference with other signals. Next, let's explore how power is distributed in an AM signal and why this matters for transmission. Power distribution in AM is a critical factor. Most of the transmitted power is concentrated in the carrier, while the sidebands, which actually carry the information, receive a smaller portion. This means that a significant amount of energy is used just to transmit the carrier, making AM less power efficient compared to some other modulation methods. Understanding these power relations helps engineers design more effective and energy-efficient communication systems. Now let's look at the different types of AM and how they address these efficiency concerns. There are several types of amplitude modulation, each with unique characteristics and uses. The main types include double sideband full carrier DSB-FC, double sideband suppressed carrier DSB-SC, single sideband SSB, and vestigial sideband VSB. Each type offers different trade-offs in terms of bandwidth, power efficiency, and complexity. In the next scenes, we'll break down each type, starting with double sideband full carrier. Double sideband full carrier, or DSB-FC, is the standard form of AM used in most radio broadcasts. In this method, both the upper and lower sidebands are transmitted along with the full carrier. While this approach is simple and easy to implement, it is not very power efficient because a large portion of the transmitted power goes into the carrier, not the information-carrying sidebands. Next, let's see how DSB-SC improves on this. Double sideband suppressed carrier, or DSB-SC, transmits both sidebands but suppresses the carrier. This means less power is wasted, making it more efficient than DSB-FC. However, DSB-SC requires more complex receivers, as the carrier must be reintroduced at the receiver for proper demodulation. This trade-off between efficiency and complexity is a recurring theme in modulation techniques. Next, we'll explore single sideband, which takes efficiency even further. Single sideband, or SSB, is a highly efficient form of AM. In SSB, only one of the sidebands, either upper or lower, is transmitted and the carrier is usually suppressed. This reduces both bandwidth and power requirements, making SSB ideal for long-distance and professional communications, such as in aviation and marine radio. However, SSB systems are more complex to implement and require precise tuning. Next, let's look at vestigial sideband, which is commonly used in television broadcasting. Vestigial sideband, or VSB, is a compromise between DSB and SSB. In VSB, one sideband is transmitted in full, while a portion of the other sideband is also included. This approach is particularly useful for television broadcasting, where it helps to reduce bandwidth while maintaining signal quality. VSB allows for simpler receiver designs compared to SSB, making it a practical choice for mass-market application. Now let's shift our focus to how AM signals are generated. There are several methods for generating AM signals, each suited to different applications and requirements. The most common techniques include the square law modulator, balanced modulator, and ring modulator. Each method has its own advantages and trade-offs in terms of complexity, efficiency, and signal quality. In the next scenes, we'll explore each of these generation methods in detail, starting with the square law modulator. Square law modulator is one of the simplest ways to generate an AM signal. It uses a nonlinear device such as a diode to combine the carrier and message signals. The output contains both the original signals and their sum and difference frequencies, which form the AM signal. While easy to implement, this method can introduce unwanted harmonics and is generally used in low-power applications. Next, let's look at the Balanced Modulator, which offers improved performance. Balanced Modulator is designed to suppress the carrier while allowing the sidebands to pass through. It achieves this by using two identical circuits arranged so that the carrier components cancel each other out. This results in a double sideband suppressed carrier, DSB-SC signal, which is more power efficient than standard AM. Balanced modulators are commonly used in professional communication systems where efficiency is important. Next, we'll explore the ring modulator, another advanced technique. Ring modulator is a specialized circuit that uses 4 diodes arranged in a ring configuration. This setup allows the modulator to produce a signal containing only the sum and difference frequencies of the input signals, effectively suppressing both the carrier and unwanted harmonics. Ring modulators are used in applications that require high-quality, distortion-free AM signals, such as in audio processing and certain types of radio communication. Now, let's move on to how AM signals are detected or demodulated. Detecting or demodulating AM signals is the process of extracting the original message from the modulated carrier. There are 2 main methods for AM detection, the envelope detector and the coherent detector. Each method has its own advantages and is suited to different types of receivers and applications. In the following scenes, we'll explore how each detection method works, starting with the envelope detector. Envelope detector is the simplest and most widely used method for demodulating AM signals. It consists of a diode and a capacitor that follow the envelope or outline of the incoming AM wave. This allows the original message signal to be recovered easily and efficiently. Envelope detectors are commonly found in standard AM radio receivers due to their simplicity and low cost. Next, let's look at the coherent detector, which offers greater accuracy. Coherent detector, also known as a synchronous detector, uses a locally generated carrier that matches the frequency and phase of the original carrier. By multiplying the received signal with this local carrier, the original message can be accurately recovered. Coherent detection provides better performance, especially in noisy environments, but requires more complex circuitry and precise synchronization. Now let's explore some real-world applications of AM. Amplitude modulation has a wide range of applications, from traditional AM radio broadcasting to two-way radio communication, aviation, and even television. Its simplicity and reliability make it a popular choice for many communication systems, especially where cost and ease of implementation are important. AM is also used in some forms of data transmission and remote control systems. In the next scenes, we'll look at specific examples of how AM is used in different industries. AM radio broadcasting is perhaps the most well-known application of amplitude modulation. Radio stations use AM to transmit audio signals over long distances, making it possible for listeners to tune in from far away. The simplicity of AM receivers and the ability to cover large geographic areas have made this technology a staple in the world of mass communication. Now, let's see how AM is used in aviation. Aviation, AM is the standard for voice communication between pilots and air traffic controllers. The reason for this is that AM signals are less susceptible to sudden signal loss due to interference, which is critical for safety. The reliability and clarity of AM make it the preferred choice for air-to-ground and ground-to-air communication. Next, let's look at AM's role in two-way radio systems. Two-way radios, such as those used by emergency services and security personnel, often use AM for communication. The robustness of AM allows for clear voice transmission even in challenging environments. Its ability to operate over long distances and through obstacles makes it ideal for mission-critical communication. Now, let's see how AM is used in television broadcasting. Television broadcasting, AM is used to transmit the video signal, while FM is typically used for audio. The use of Vestigial Sideband (VSB) modulation allows for efficient use of bandwidth while maintaining high picture quality. This combination of AM and FM ensures that viewers receive both clear images and sound. Next, let's explore AM's role in remote control systems. Remote control systems, such as those used for model airplanes and cars, use AM to transmit control signals. The simplicity and reliability of AM make it suitable for these applications, where quick and accurate response is essential. AM's ability to penetrate obstacles and cover reasonable distances adds to its appeal in remote control technology. Now, let's look at AM's use in data transmission. Though not as common as other methods, AM can be used for data transmission in certain applications. For example, some telemetry systems and early computer modems used AM to send digital information over analog channels. While more advanced techniques have largely replaced AM for data, it still finds use in specialized systems where simplicity is valued. Next, let's discuss the advantages and disadvantages of AM. AM offers several advantages, including simplicity of implementation, low cost, and the ability to cover large areas with relatively simple equipment. Its compatibility with basic receiver designs makes it accessible to a wide audience. These strengths have ensured AM's continued use in many communication systems, despite the availability of more advanced alternatives. Now, let's consider some of the drawbacks of AM. Despite its strengths, AM has some notable disadvantages. It is less power efficient than other modulation methods, with much of the transmitted energy going into the carrier rather than the information-carrying sidebands. AM is also more susceptible to noise and interference, which can degrade signal quality. These limitations have led to the development of more advanced modulation techniques for many modern applications. Next, let's summarize what we've learned so far. We've covered the basics of amplitude modulation, including its time and frequency domain representations, modulation index, bandwidth, and power relations. We've also explored the different types of AM, methods for generating and detecting AM signals, and a variety of real-world applications. Understanding these concepts provides a solid foundation for further study in communication systems. Next, let's look at some historical context for AM. Amplitude modulation has a rich history, dating back to the early 20th century. It was the first method used for audio broadcasting and played a key role in the development of radio technology. The simplicity and effectiveness of AM made it the standard for decades, shaping the way people communicated and consumed information. Even today, AM remains an important part of the communication landscape. Now, let's look at how AM compares to other modulation techniques. AM and FM are two of the most common modulation techniques. While AM varies the amplitude of the carrier, FM varies its frequency. FM offers better noise immunity and higher sound quality, which is why it is preferred for music broadcasting. However, AM's simplicity and long-range capabilities make it suitable for talk radio and emergency communication. Each method has its own strengths and ideal use cases. Next, let's discuss the future of AM. Though digital and more advanced analog modulation techniques are becoming more common, AM continues to be used in specific applications where its strengths are needed. Advances in receiver technology and digital signal processing have helped improve AM's performance and reliability. As communication needs evolve, AM is likely to remain a valuable tool, especially in areas where simplicity and coverage are priorities. Now, let's look at some key terms related to AM. In AM, the carrier is the high-frequency signal that is modulated to carry information. Sidebands are the frequency components above and below the carrier that contain the actual message. Understanding the roles of the carrier and sidebands is essential for grasping how AM works and how different types of AM optimize efficiency. Next, let's define the concept of demodulation. Modulation is the process of extracting the original information from a modulated carrier wave. In AM, this involves recovering the message signal from the amplitude variations of the carrier. Demodulation can be performed using simple circuits like envelope detectors or more complex methods like coherent detection. Understanding demodulation is crucial for designing effective communication systems. Next, let's look at the concept of bandwidth in more detail. Bandwidth is the range of frequencies that a signal occupies. In AM, the bandwidth is determined by the highest frequency in the message signal and is doubled due to the presence of both upper and lower sidebands. Efficient use of bandwidth is important for maximizing the number of signals that can be transmitted in a given frequency range. Next, let's discuss the importance of power efficiency in AM. Power efficiency refers to how effectively a communication system uses its transmitted energy. In AM, much of the power is spent on the carrier, which does not carry information. Techniques like DSB-SC and SSB improve power efficiency by reducing or eliminating the carrier in one sideband. Power efficiency is a key consideration in designing modern communication systems. Next, let's look at the role of noise in AM. Noise refers to unwanted signals that interfere with the transmission and reception of information. AM is particularly susceptible to noise because any variation in amplitude, whether from the message or from interference, affects the received signal. This is why AM broadcasts can sometimes sound static-filled or distorted. Understanding noise and how to minimize its effects is crucial for reliable communication. Next, let's discuss the concept of modulation depth. Modulation depth, closely related to the modulation index, describes how much the carrier amplitude varies in response to the message signal. Proper modulation depth ensures clear transmission without distortion. Too much depth can cause overmodulation and distortion, while too little results in a weak signal. Balancing modulation depth is essential for high-quality AM transmission. Next, let's look at the importance of synchronization in AM system. Synchronization is especially important in coherent detection, where the receiver must generate a carrier that matches the frequency and phase of the original transmitted carrier. Accurate synchronization ensures that the message is recovered correctly and without distortion. This is particularly challenging in mobile or rapidly changing environments. Next, let's explore the impact of AM on modern communication. Amplitude modulation has had a profound impact on the development of communication technology. Its simplicity and effectiveness paved the way for mass media, emergency communication, and global connectivity. Even as newer technologies emerge, the principles of AM continue to influence the design and operation of modern systems. Understanding AM is essential for anyone interested in the field of electronics and communication. Next, let's look at some practical tips for studying AM. Master amplitude modulation. It's helpful to work with both theoretical concepts and practical experiments. Building simple AM circuits using simulation software and analyzing real-world signals can deepen your understanding. Reviewing key equations and practicing with sample problems will also reinforce your knowledge. Next, let's look at some common mistakes to avoid when learning about AM. Uncommon mistake is confusing the roles of the carrier and sidebands. Another is overlooking the importance of proper modulation depth, which can lead to distortion or weak signals. It's also easy to underestimate the impact of noise and interference on AM performance. Being aware of these pitfalls can help you avoid errors and gain a clearer understanding of amplitude modulation. Next, let's explore some advanced topics related to AM. Advanced topics in AM include digital amplitude modulation, adaptive modulation techniques, and the integration of AM with digital signal processing. These areas push the boundaries of what AM can achieve, enabling more efficient and robust communication systems. Exploring these topics can open up new possibilities for research and innovation in the field of communications. Now, let's wrap up with a final summary. Amplitude modulation remains a cornerstone of communication technology. Its principles are simple yet powerful, and its applications are diverse. By understanding AM, you gain insight into the foundations of modern electronics and communication systems. Whether you're studying for exams or working in the field, a solid grasp of AM will serve you well. Thank you for joining us on this journey through amplitude modulation. If you're interested in learning more, consider exploring related topics such as frequency modulation, FM, phase modulation PM, and digital communication techniques. Each builds on the concepts we've discussed and offers new challenges and opportunities. The world of communication technology is vast and ever-evolving, and your journey is just beginning. Keep exploring, keep learning, and stay curious about the signals all around us.